There we go. All right. Well, hello, everyone. We're back for the afternoon. This is supposed to mostly be Q&A, but Jade did ask us about maybe going through how to start a new planet. And I was reminded by Stephanie Olson that we actually have a document on how to create a new planet, which I had forgotten about because I never need such things myself. That's one of the perils of using a model too much. And so I thought we could just quickly go through this document, and we'll put a link to it on the Simplex site where you download the code, and I will try to share that with you. But maybe before I do that, maybe I should just ask if there are any other questions that we can answer for people that we didn't get to or came up later or things of that nature. Is there any other questions about things that we could cover? Yeah, Colby?
I had a question when you were referring to making sure the star is compatible with the shortwave spectra. I was wondering if you could just show an example of like where to look to make sure that. Yeah,
I can do that. Let's see. Off. Can we turn the screen back on?
Here.
Oh, there it is. Yes. Let me share the proper screen. Let me try it this way. Okay. So as I said, you should have downloaded this one instead. All of the spectral files document, all the spectral files, and that should be hiding in this Model E support directory, if you remember. And then there should be a Socrates subdirectory, and hopefully you have some file structure similar to this. And then here you can see where all the spectral files are. And then these names are the names that you see. The directory names here are the same names you see in the spectral files document. So let's say we go into one of these, like this SPSW in shortwave, DSA ARCC. And if you do an LS in there, you can see exactly what I'm talking about. You can see if you want to use this particular shortwave file for this particular spectral file set, the only stars that are in here are PC, Proxima Centauri, our sun 2.9 gigayears ago, and that's it for this. That's the only those are only stellar spectra that you can use with these particular spectral files. So you have to go into this spectral files directory, and again, for each one of the SP_SW associated spectral files, you have to check and see if the solar spectrum is in there. The other way you can do it is you can just give it a try, and your code will probably not compile or bomb or something like that, and you'll see, hey, something like, this file does not exist.
Oh, it will compile it. It's just when you run it.
Yeah,
file is missing.
Exactly. So yeah, it will compile, but it will tell you the file's missing. If you're lucky, it will tell you the file's missing. Sometimes you get these funny messages that say, input file not found, but it doesn't tell you which input file. And you have like 30 input files in these run decks. So then you're going to have to go into debug mode, and then you're going to run the model and hope the model tells you what input file it is that you have not included.
.prt file usually tells you, huh?
I would say that that's not the case for me anyway. Most of the time, the PRT doesn't tell me.
That's weird. That's weird, yeah.
But for a spectral file star combination that is missing, it is possible in general to create.
Yeah, we have documentation for that, and it will also depend upon Eric's free time. We can't do every time those things, but
making a single spectral file for a star that already exists in the database, for a spectral file set that already exists in the database, is not a big commitment of my time. Hey, Eric, could you run this? And then it takes me a few minutes to set it up. I press go, and then, you know, anywhere from 4 to 8 hours later, voila, it's there. So.
Is that clear? Cool. Okay. Anything else that we can help people clarify? Yeah, Daniel.
Single column version was mentioned somewhere in the document.
Yes, and we did not.
Somewhere that it's
We skip the slide.
We skipped that because it's not really ready for prime time. In theory, that will come out with hopefully soon after we get Planet 2.0. Tony, you've been pushing that from your side.
It exists for an ocean underneath rather than a land. 3 box underneath. I've been trying various things to come up with a way to make the single column model climate look like the equivalent 3D model climate. I haven't found a way to do it. And even for, never mind synchronously rotating planets, you know, for which you've looked into 2 column model, but even for a rapidly rotating planet, clouds, the water vapor profiles that are dramatically different from the Earth, no matter where on the planet I choose to look at it, and then try putting in fake dynamical fluxes to remedy that. So far, I haven't been able to do it. So I mean, so there is a version there, and it's usable, but don't think in its current form that it will give you something. And admittedly, I haven't spent a lot of time thinking about it.
Okay. Mike, what is the planned release schedule for Planet 2.0? I've heard you mention. Oh, this will be fixed in Planet 2.0.
Well, we thought last year around this time we would have it done by the fall, and we didn't manage that. Things happen. Kostas and Tony have been in charge of most of that. Kostas, where we stand.
So where we stand is that unless a surprise shows up, it's ready. So we're finishing now the test simulations we're doing, essentially the very long simulations for all individual templates that we will be supporting, and checking the results. Nothing showed up so far. The only thing that we have not started, but it should be fine, is the coarse resolution of the atmosphere and the ocean. And we will start them by the time I will get the reply to an email. And then, but everything else, fixed SSTs for
Fixed surface temperatures.
Yeah, fixed surface temperatures with the GIS and the Socrates radiation for the fine and medium resolution versions of the model is done. The same thing for the Q-Flux Ocean, all those flavors is done. The dynamic ocean with the fine resolution, which is 2 by 2.5 degrees in the atmosphere and the 1 and the 1 1/4 in the ocean, is running as we speak. Actually, literally, I was just, and there are no surprises there. So code-wise, yeah, again, unless something shows up that we do not expect, it's done.
And for 3 different control.
And yes, and for 3 different planets. Yeah, one
Earth model.
One is exactly the present day Earth. The other is a planet that the atmosphere that we're working these 2 days, which is no aerosols, no ozone, no stratospheric water formation from methane oxidation. And the third one, which is new, and it will be probably our working horse, is 100% nitrogen atmosphere plus trace gases like CO2 and stuff. So we took out oxygen and argon, and also it doesn't have, of course, ozone and aerosols.
If you look at the exoplanet GCM literature, they're the mix of things that people just generously refer to as, you know, we used an Earth-like atmosphere, and then you have to read the details. So we have sort of 3 options. We have a real Earth atmosphere, the aerosol.
Yeah.
ROCKE-3D,
unless you're using it for paleoclimate.
So it sounds like the answer to my question is imminent, pending any surprise.
And so when that comes out, is the way that we use it going to be similar to what we've been learning in this workshop?
Exactly the same.
You'll go to Simplex, download the tar file, extract it, and start working with the new templates.
It'll just say Planet 1.0 instead of Planet 2.0. Or 2.0
Yeah,
instead of 1.0. It will have both there. You can still run 1.0.
And the random names we'll have a few more letters there to describe properly all those different scenarios that we're supporting. So we are working on P1SOM40. So that will become P2. The S will be S or G. G for GIS radiation. The O can be nothing, Q or O, as we have here. The M can be M or F, F for final resolution, and then we have another letter for the atmosphere type. But everything will be explained in the documentation is updated in the template.
Templates will actually have proper documentation.
It's literally ready to go until something really unexpected shows up.
We're very close. Yes.
And unlike Planet One, where you only run it at 4x5, this one will still have a 4x5 option for the atmospheric ocean, plus a finer resolution 2x2.5 atmosphere 1x1.25. So that will be different than if you run that.
And of course,
If you have a rapidly rotating planet, magnitude more computing time.
and of course, it has greatly updated physics in several respects, which are probably beyond the scope of discussing them right now. But it is at least 3 years of work on the Earth side of the model that has been propagated into the Planet 2.0.
Any other questions? Okay. I guess Jade was saying she would be interested in us going through how to create a new planet. And as I was mentioning, Stephanie Olson reminded me, I actually have a document written by Chris Kalos, one of our postdocs, that actually does this. So I thought we could just go through a bit of that, if that's okay with you, Chris. You're here, so if I say something incorrectly, you can correct me. Otherwise, say, no, don't do it that way. So let's take a look at that. Maybe I can go full screen, I don't know. That didn't make any difference, but okay, anyway.
As a matter of fact,
Yeah.
just totally random, the simulations that you've seen in the balancing slide are from Planet 2.0, what we're doing right now. Just a random fact.
Where would I have to go online to find this document and the radiation document you showed earlier?
They are in, if you go to simplex.gis.nasa.gov, where you downloaded the model from, those documents are there now. If you click into the ROCKE-3D planetary GCM page, and this document we haven't put up yet, but Igor will fix it this afternoon. He'll fix the link. I sent you an email link about this, so he can't do it from his computer here, but we will add this creating a new planet link this afternoon. Also on that page. So everything should be linked from the page. I can go there quickly if you want to. If you go to simplex.gis.nasa.gov/GCM, and if you go to GIS ROCKE-3D planetary GCM, you can see all this stuff here. Model crash FAQ, which we mentioned. There are actually ROCKE-3D, and I think that's the installation instructions you all have. Tools needed to change the stellar spectrum. That's in there. User guide to spectral files we discussed already.
That's more generic.
Yeah, this is more generic stuff. Spectral files needed to run. That's the same document, and or to download, and then the latest release. So we will add one more line here on how to create creating a new planet. We'll go through this document. Will be available.
Was there a document that gives an overview of the stuff you were talking about yesterday, and like how to convert that net CDF output, like all the stuff with the AIJ?
You have to look in the tutorial slides for that stuff. There's no document for that. I mean, there is a document written by the Earth people, but it's embedded in a much larger document. It's kind of messy. I think it's better just to look for the slides.
And this is all being recorded, right? So
Yes.
there will be something on YouTube.
You can always scan the YouTube channel, and you can find exactly what we talked about, hopefully.
So could we also have a discussion board?
Yeah, we actually have, by the way, so I meant to mention that earlier, but I didn't get a chance, and I'm glad that you brought that up. So we actually have created a Google Groups group for discussion for this model. We created it last year after the tutorial, and it was never used by anybody.
So there were no problems.
Yeah, so everything works great.
Yeah.
But we had a few things on it, but people, I tried to tell people, please write the group and they will reply. So everybody's replies and questions stay up there, and so answers can be found. But people asked us a few questions and they never posted there. So we would ask, I'll share that with you later. We would ask that people post to that group questions and that we can answer them. And then they're archived automatically and anybody can see those answers. So yes, we have that, and I will add everyone's email that I have for you to that Google group. And if you want to be removed, I'll remove you. So does that sound okay? Okay, I will do that.
I mean, if someone send a question, will everyone get it?
Yeah.
Then some people might not send the question.
It's the fastest way to get an answer, because we are really busy, and usually the questions you might have will require us to check things probably, unless it is something really trivial, but it's the fastest way to get an answer.
Yeah.
If you're worried about like a stupid question, because there are no stupid questions with something as complex as CPM. I think we all appreciate that these are pretty opaque things to try to learn and use, and that.
And if you worry about
any question is a good question.
And if you worry about spam, it's a really quiet group, I'm telling you that.
No one has written to the group since last year, basically. So it's very quiet. But yeah, there's no bad questions or anything like that, because the model, as it's very complex, and as we say over and over again, very poorly documented in general. We are trying to rectify that in some ways. But this group, a discussion in this group could help rectify that, because if there are obvious things that we should document or mention in some way, we can do that. And that will be useful for everyone, actually.
I mean, and doing this is kind of forcing us to slowly, excruciatingly document various aspects of the model. So, over time, it actually helps us.
Yeah, the Earth model of the side of the house doesn't run tutorials like this, basically. It's all based on one-on-one interactions with scientists here. That's how it's typically been done. So we're really we're kind of the guinea pigs in a sense. We've done this now for 3 years. And maybe we're getting better, I hope, and creating more documentation and more ways to learn how to use the model. But we need you also to participate. So please, give us your questions. Don't be afraid. Don't be shy. There are no dumb questions. Yeah, Colby.
So when we look at the Panoply page at an AIG file, do they have any like temperature pressure profiles in there?
Yeah.
Not AIJ.
Oh, no.
No.
So temperature pressure, say, profiles you can get from AIJL file. And there's also an AIJK file that probably has temperature also, but AIJK is more oriented towards general certification qualities like zonal profiles and stuff like that.
And it doesn't really have three-dimensional pressure, but it has the information you want to calculate it yourself. And then the way you calculate it now is you need to do some math based on the sigma levels and the surface pressure, which changes with time. And then for planet 2, this has changed. So we will be providing planet 2 the air mass in 3D. And from that, you can easily calculate the surface pressure. You just divide by gravity.
Yeah.
And
Again,
then you get the delta pressures.
this page in the slide set that you have does have pointers to documentation that we have tried to write for a lot of the diagnostics in a few of the files. So the AIJ file, we have a Google Doc that we have tried to fill out. We haven't filled out everything. The AJL also, and the AIJL, which was just mentioned, is also there. We just don't have the resources to do every single diagnostic, but we've tried to tell you what most of these things mean.
The most common ones, anyway. Like if you looked at that AIJ that Mike put up yesterday, it's got a zillion different variables in it. So we've tried to make.
Yeah, we can look at it quickly.
A decent fraction of them that are probably among run across. But if you have questions about things that we haven't described here,
Yeah, it's a sheet, so it's a Google Sheet, so you can, we tried to put everything. I think that Tony wrote most of these in his infinite spare time.
Which is why I never got finished.
So there's a lot in here, not everything, but the major things are documented.
And there's like quirks to a lot of these variables. There are, the problem with the diagnostics in the model is that the Earth modeling group consists of many people over many years who have passed through the modeling group and put their own things into it, and everybody adds diagnostics, no one ever takes diagnostics out, and everybody comes to it from their own point of view, and so different people think that should be the same as some other variable in the model, but that there's an AIJ thing for it. And it tells you what the units are, but the units aren't always consistent. The sign conventions aren't always consistent. One thing you need to know about GCMs or Earth science studies in general is that there are energy fluxes through the atmosphere coming in from the sun or the star and then going out as thermal emission. And Earth people tend to define the sign of energy fluxes as positive. Positive means a warming effect on the system. So downwelling starlight is a positive flux. Upwelling thermal radiation is a negative flux. But some of the diagnostics in the AIJ file follow that convention, other ones don't. So I've tried to like make notes when I think that things are a little wacky, just so people have a heads up.
Yeah, look, also, I think it's really important to look at the units people use. There's a complete inconsistency in the use of units in these diagnostics. So don't assume because you used one specific humidity quantity for one of these things, that the next one for a different layer, for example, use of the layer, like if you have 100, 200, 300, those will be the same, but maybe QSurf or QATM or something else may not have the same units. So look very carefully. Are defined usually what the units are, but sometimes you have a case where it'll say 10 to the minus 4 grams per gram for, say, a specific humidity amount, instead of gram per gram, which is what you think it should be. So be very careful. I myself got burnt on this a couple of years ago, and I only found out about it because I talked about some results in the group, and then Yuka mentioned, oh, by the way, did you make sure that you used the right units? I thought she was crazy, and then I looked at it and it was like, she's right.
Right there, liquid water path, line 6.
Yeah. So be very, very careful when you are using these things to make sure the units are what you think they are.
And again, ask us through the Google Group or whatever if you're not sure about things. One other thing just to point out, in the 3D files, the AIJL and the AIJK files, right? So the model computations are done on sigma levels. So that's the actual place where the variable temperature, whatever, is calculated. The actual model profile of temperature as a function of sigma, which is kind of sort of a normalized pressure variable. But for a lot of applications, people would rather have things on standard pressure levels, 850 millibars, 700 millibars, or whatever. And so in the AIJK and AIJL files, there are some variables that are given to you as a function of model layer, which is the native, the actual thing the model is calculating. And then you might find a second version of the same variable in the same file that is now given to you on pressure levels.
Yeah, I see that right here, actually.
Standard pressure levels. The standard pressure levels are very convenient, but occasionally they can get you into trouble. And so we found, like, at high latitudes on very cold planets where there is a near surface inversion layer, and the model interpolation routine is trying to map from a model layer to a standard pressure layer. You look at the temperatures on the pressure level, and they seem to be completely inconsistent, especially near the ground, with the temperatures on the actual sigma level. And it's just because it's not a good mapping for some of these stranger meteorological situations that nonetheless you can encounter on cold planets near the surface where sharp temperature inversions are very common. So you have to be careful when you look at things like that, and anything that you want to look at on a model variable maps to standard pressure levels, you should probably also look at the same variable on the actual model layer level, just to make sure that you're getting the right picture of what the model is actually doing. Thank you.
Ask questions. Any other questions? Take a look at Chris's document here.
I was going to say, is there anything in your document about initializing the model?
Yes, because I think it's towards the bottom, but it's the iStart because I think we mentioned yesterday, you only really need 2 or 8 for most circumstances unless it crashes.
Yeah, we talked about that yesterday.
How straightforward is UCAS model to use?
Well, she has a documentation page, and I think it's pretty good because many of us wrote her and asked her to explain more and more and more.
Maybe Sonny can answer that.
Yeah, Sonny, how do
Because
you?
you've used it, right? The UCAS model?
Yeah.
How straightforward is it?
You've been using her document, I can figure it out.
I've been using her document, and it's relatively straightforward. There's a few quirks, but mostly because I'm not a fluent Python user yet. But mostly the investment is just running the model with the larger number of spectral bands to get the resolution you need to do the spectra. So
It's pretty straightforward. I mean, I've used it.
yeah, the guide is fantastic.
Going back to the initialization thing, so I was actually thinking not of the model iStart variable, but a strategy for initializing your model for various problems, right? This is an Earth-based model, and people usually start it with some modern Earth climate as the starting point, although you can start with something simpler like an isothermal atmosphere if you create it for yourself. But when you get to exoplanets are new worlds that we don't know anything about, and so it turns out that some types of planets that you might construct might be sensitive to what you choose as your initial condition, and other types of planets might not. We have not done a thorough exploration of that, but for example, Chris has a new paper he's about to submit looking at high obliquity planets, and those can give you different answers depending on whether you initialize it with a moderate climate with lots of liquid water, or whether you initialize it with a snowball state. And so you have to be careful sometimes in what you do as to whether the result you're getting is a unique result given the initial condition that you've chosen. And this is a topic of discussion in the exoplanet community already. Jade has a paper on that for tidally lost planets around M stars, right? So we did one Proxima B simulation where we started it, instead of starting it with warm atmosphere, round up in the same place, which is what your paper predicts should happen, but we haven't done a thorough exploration of that ourselves.
We did that.
Yeah.
We duplicated her original plasma paper with Rocky, and we confirmed that result.
And you get the same result. Okay, that's great. So but there are a subclass of planets that the initial condition will matter, and you should just be aware of it.
So just to add to that, so there's 2 things. One is whether you started, what your initial conditions are, and that'd be one case where you do iStart. Want to use that snowball as the initial condition for a new experiment. That's an iStar 8 example. The other thing with the IC files, AIC or OIC, is if you can start at, say, 285 Kelvin or 300 Kelvin. If you suspect your planet is going to be cold, you might want to start at, a colder temperature, maybe not freezing, but, just because it'll take quicker to get to equilibrium. I don't know if you talked about equilibrium.
We did talk about it, yes.
If you start in a climate that's 10 degrees, removed from what the equilibrium result will be versus 1 degree removed from that, then it could take many days. It could save you many days of actual time.
Assuming you know where it's going to end.
Well, yeah, sure, but if you run a planet that you know is going to end up cold, sensibly about those choices.
And if you have a dynamical ocean, it's helpful to start warmer and cool your planet down than to try to warm your ocean up because of the thermal stratification of the ocean.
Another thing, when you make a snowball planet, so the dynamic ocean includes sea ice advection, and usually the sea ice advection scheme does just fine when it's just pushing chunks of ice out into the open ocean or off the Arctic or through the France Strait or something like that. On the other hand, when you get to these colder worlds where you start out with ice at high latitudes and then you're running them with lower insulation or reduced greenhouse gases or whatever, and the ice sheet starts to come down and eventually get to the point where you create a full snowball. Apparently the sea ice advection has some problems as things close in on the open water and things, I guess, start bumping into each other with the advection, and we have it. And so you will see that in your snowball planet as a kind of semi-checkerboard pattern in things like the sea ice cover or things like that. We think that that's probably a problem that could be solved with a shorter time step for the sea ice advection or something like that, but it's a problem that we haven't solved yet in ROCKE-3D. So if you do simulate snowball planets with oceans, you might see some weird looking things near the equator that look like a numerical problem. I think they probably are.
I think that applies for a lot of things. If you see checkerboarding, stop and reevaluate. It appears lots of other places, not just sea ice.
Ken, yes.
Yeah, I guess I wanted to mention again, returning back to diagnostics, one of the diagnostics that people mostly look at is surface air temperature, which is convenient, but unfortunately, this is like not the major diagnostic in GCM, in the sense that this is derived quantity. Like the main quantities in the GCM are ground temperature and then air temperature, layer temperature. And surface temperature, air temperature is interpolated, and it's interpolated based on what planetary boundary layer model is thinking about the boundary layer. And sometimes what it's thinking about it may be not quite correct for conditions completely different from Earth conditions. So whenever you think that your surface air temperature might look strange, try to look at ground temperature and lower atmospheric temperature, because those will be more basic things. And often, even if planetary boundary layer is not working very well, you still get correct climate. For example, when you have stable certification most of the time over certain areas, basically you have no flux, so it has no effect on real climate. But your surface temperature may get kind of crazy because of that, because it decouples from the ground. So that's one thing to remember, that surface air temperature is convenient, but it's not the main thing that GCM produces.
Can I make a comment about coming into energy balance, radiation balance in the model? So Mike Costas said this morning that we generally try to ask the model to get within 0.2 watts per square meter plus or minus of being in balance at the top of the aperture. There's nothing magical about 0.2 watts per square meter. It just seems like a goal below which it's not worth exerting more effort to try to get the model into balance. So when we create our Earth models, if we're within plus or minus 0.2, we say that's good enough. It turns out, surprisingly to us, that the worldwide community of Earth climate models has a lot of trouble with that. And out of the 20 some odd or so GCMs, Earth GCMs that there are around the world, maybe a third of them actually get that closer to energy balance. And there are some operational climate models out there that are 2, 3, even 3.5 watts per square meter out of energy balance, which suggests that something is not being conserved somewhere in the model. So we like to try to do better than that. But for exoplanet, applications. Again, we're going into regimes that we haven't been in before. Every once in a while, we'll have a model run that does not get to within 0.2 watts per square meter. It gets to within 0.5 watts per square meter, or even close to 1 watt per square meter, and it's in steady state. It's not changing with time. It's just not getting any closer to zero. And so there may still be a couple of things in the model that are a little bit weird that we haven't quite figured out yet. So just to warn you, it's possible on some more exotic planets you might encounter that. If you encounter that and figure out what we're doing wrong, we would love to hear about it so that we can fix it. But every once in a while, you find that problem. Another thing that we find occasionally is that the temporal evolution curves that Mike showed you this morning are not always as well behaved as the one that he showed you. We had one case in particular for an exoplanet where there was very significant variability, much larger variability from year to year than the typical planet that we look at, and sometimes variability on multi-decadal timescales. And so there was one such case that we ran that showed that, and we looked at a zillion different things for reasons for why it might happen, and we kind of concluded, and I don't know whether we've proven this or not, but we sort of concluded that we just happened to be running the model near a boundary between a transition between two fundamentally different dynamical states. There have been a number of papers in the literature now about the dynamics of synchronously rotating planets that suggest that there are probably at least 3 different dynamical regimes depending on, well, most people think of it as depending on rotation period, going from slow to fast and then another regime in the middle. But actually, it's more fundamentally as a function of what the Rossby radius of deformation is on the planet compared to the actual size of the planet that you're looking at, and rotation is only one of the things that affects that. And it turned out this one run that we were doing just happened to be at a place that we think is at the boundary between 2 of those different regimes. So we think that what was happening is that due to the normal internal variability of the model, it was sort of on decadal or multi-decadal timescales, kind of just like slipping back and forth between these 2 fundamentally different dynamical regimes. We haven't proven that. We proved that enough to get the reviewers to accept the paper, but I don't know that we actually know that that's what was going on. But we tried to make an argument that that's what was going on. Depending on what you do, what planet you run, you may occasionally find funky behavior like that in the model that at this point we think is real behavior, not a model flaw, but just beware.
Which case was that?
So it's one of the Proxima Centauri B cases. And so we ran Proxima Centauri B with a bunch of different atmospheres to see how much we could change things. And our normal atmosphere was an Earth-like atmosphere, N2 and CO2, moderate CO2. And then we ran a couple of cases of Archean Earth-like atmospheres, but on the Proxima Centauri B setting. But we took Benjamin Charnet's set of cases with different CO2 and different methane, and then put those into the Proxima B planet. And when we ran his low CO2 case, everything looked just fine.
Right.
And then we went to the higher CO2 plus methane, and I thought we were going to get a warmer atmosphere out of that, but actually we got a colder atmosphere from that. And it turns out the colder atmosphere is due to the methane absorption in the upper troposphere. And because the methane is absorbing in the upper troposphere, what are you doing? You're stabilizing the lapse rate of the atmosphere compared to the case without any methane in it. And when you stabilize the atmosphere, you increase Brunk isola frequency, and therefore you increase the Rossby radius of deformation. And we went from a run basically by changing the methane and increasing the CO2, but mainly by changing the methane, we went from a situation in which the Rossby radius of deformation was smaller than the size of the planet to a case where the Rossby radius of deformation was larger than the size of the planet. And when we looked at all the general circulation variables, everything was different, in suggesting that we actually had switched dynamical regimes, consistent with a couple of other papers that are out there about, like there's one by Jacob Hock-Misra that's out there? You're probably hoping
Well,
for that, right?
I was going to ask.
One by NODA.
This isn't in Jacob's paper, but in the meantime, for those cases for Earth-like planets around 3,000 K-stars, we found some weirdness about initial conditions toggling back and forth between our rapid rotators and an in-between state that we don't really have any explanation for other than initial condition problem toggling between states. That's why I was curious. It seems to be, they're not exactly proximal, but it's in that same ballpark.
Right.
So that's interesting to me that you guys have the same thing going on.
We actually talk about that in the paper and show plots.
Okay, is that in the proximal paper?
In the proximal
Okay,
paper,
I'm gonna have to dig and find that. Yeah, thank you.
So we don't know that that's the explanation, but.
Well, yeah, we haven't published the weirdnesses we found because we found them after Jacob's paper, and switching between different supercomputers and slightly different initial conditions, a few different cases would go either this way or that into different dynamical regimes. So,
and you know, and that's methane for you, right? So methane is a little bit of a weird gas, as people have noticed that on Titan it's playing that role. Ramses Ramirez has written papers about the role that it might be playing on exoplanets. You definitely see that because it absorbs. You put methane into an atmosphere with an N star. Irradiating it, then you get all of this heating in the upper troposphere, and that actually has a noticeable effect on the dynamics. So expect weird things to happen. It's like that's the overall message. And some of them will be real, and the challenge is figuring out which ones are real, separating which ones are real from which ones might be a model problem.
Okay. Any other questions people want to ask? I think going through Chris's document might take a while. Should we take a?
There is a question which is good online. What is the difference between pressure variables and model level variables? Tony mentioned it. I don't know if this question was asked before or after that, but essentially model variables, pressure variables are constant pressure level, so there is some interpolation going on, and then for every grid cell in the model, you get the diagnostic in a specific pressure. And model level variables means that this is output on the native grid that follows topography because of the sigma layers.
Yes, and in diagnostics files, when you view them, you will see that you have data everywhere for model layers, but for constant pressure layers, you will see that data disappears on lower layers because of high topography, where it's basically just blocked by topography. So you'll see gray areas.
And most of the time, a letter of L means model layers, and a letter of K means pressure level. So AIJL is model levels, almost always, except when it is obvious from a variable name, and AIJK is pressure levels. AIJK is being removed, right?
Is it? Might be.
I don't know.
I think so.
Is it?
Well,
and things migrate into AIJL.
Well, I noticed that an AIJL has both actually.
Yeah, I think that they eliminate slowly the K one.
And I haven't used K for a while.
And the thing is, you know, the model variable on model levels, that is the fundamental thing that the model is calculating. So that's the real model. The interpolation to constant pressure level is a convenience for meteorological interpretation of things that most of the time is okay, and every once in a while gets whacked.
Yeah, so I was saying that I think to go through Chris's document might take a little while, so should we take a little break? And then we'll come back and try to get through that and get through questions.
So we'll run an example, right?
Yeah, we'll go through his example. We're going to go through Chris's document.
Oh, okay, but are you actually going to create the climate?
Oh,
in real time?
To do that at the same time.
But I think that's what Jake was looking, right? Was asking to do, actually.
Well, let's see how this document goes, and then we can do it.
Should do that.
Sure. It doesn't matter. Okay, so we take like, we meet at 3 o'clock. That's like 12 minutes from now. Sound good?
Okay.